here, and today I will sketch a very general overview of my research that I have done in the institute. First, I will start with a very general motivation of quantum technologies. What are the differences between classical and quantum information, the challenges to control quantum systems, and the long-term goals in the field. And at the end, I will summarize my research line and the most important recent results that I had. Will be very general. The idea is to just to know each other, so you don't expect very concrete technical details and so on. How you? Oh, there's a technical problem, I think. Murphy's law. Huh? No, the slides do not. Okay. Well, so I start with the difference between classical and quantum information. So imagine a hard disk. A hard disk is made of magnetic domains, and if it is up or down, we can store a 1 or a 0, and this can encode in this way classical bits of information. This we have in many computers and in our cell phones. And if you have a quantum register of n of these bits, then we can store one configuration of a total of 2 to the n possibilities if we have n of these domains. Okay, now imagine now a quantum system like an atom, and in this atom it can have different states. For instance, the ground state, and there can come a scientist like us and shine a laser and put the atom in an excited state, for instance, or the electron there. And we know from quantum mechanics, from Erwin Schrödinger, that in nature it is possible to have superposition of different states, and where the coefficients there are interpreted as probability. And the step now from quantum information comes that here, if we it's complicated. Well, yeah. If you store a 0 in the ground state or a 1 in the excited state, then this superposition you can interpret it as a qubit, like the basic element of quantum information. And the quantum power comes from the superposition principle. Imagine now that you have a quantum hard disk with n of these qubits, and the quantum mechanics allow you to have a superposition of 2 to the n possibilities all at the same time. And if you store now one or a 1 in the ground excited state and 0 in the ground state, then you can have a very huge parallelization of an exponential number of configurations all at the same time. If you have n qubits, you will have 2 to the n possibilities at the same time in your quantum hard disk. This is like the quantum power that is hidden in a quantum device. And for example, if you have 300 qubits, only if you could have 300 qubits in the hard disk, quantum hard disk, you can store 2 to the 300 complex number, which is on the order of the atoms in the visible universe. So it's really, this is the power of the quantum power that is there. And quantum technologies is about, the big challenge in quantum technology is about to exploit this quantum power to perform tasks more efficient or impossible for classical devices. And one can classify this as quantum hardware and quantum software. Hardware is really the challenge to build these quantum devices in practice, like quantum machines that can manipulate these superpositions. And quantum software is, the task here is to design quantum algorithms that take advantage of the superposition principle to be efficient. For instance, the factorization of prime numbers in polynomial time is called the Shor algorithm. And in my talk, I will concentrate mainly on quantum hardware, which is what I work more. Well, the challenge of building quantum devices is actually very hard, because quantum superpositions are very delicate. Okay? So imagine now we have a quantum system built of 2 atoms that I have there, and this always will be interacting with some environment. And a scientist here needs to control and measure the quantum system. Therefore, you always need an environment. You cannot get rid of the environment, because also we need it to control and measure it. And so we need a very precise control over this quantum system and high isolation to avoid that the atoms here get decoherent, so they decay, basically. If they have spontaneous emission, for instance, they will decay, and you will lose your superposition. So you want to control the quantum system to avoid this to happen, or to make the operation much faster than the time that this can happen. And the other fundamental requirement is that we need to control the interactions between a quantum system. For instance, here the two atoms, we can couple them to an optical cavity and use this to make engineer interactions between them and create entanglement. If you create an entanglement, means that we can control these prefactors we have in the superposition. For instance, the C2 and C3, we can make it 0, and in this way build an entangled state, for instance. This is a state that cannot be obtained as a product of two independent atoms. So, and has very special properties that are not in classical physics, and this is where we can get an advantage over the classical physics. Okay? So I said that controlling quantum systems is very hard, but actually it's a reality right now due to a great scientific and technical progress in laser cooling and trapping, precision spectroscopy, and so on. And there was a Nobel Prize in physics in 2012 to Dave Weiland and Serge Haroche for this. So Dave Weiland was for doing these experiments and manipulating these superpositions in trapped ions, which are basically charged atoms trapped in electromagnetic fields, and they use lasers to control the states of the superpositions. And Haroche is funny that it's the opposite. They do exactly the complementary approach. They store quantum information in photons inside cavities, and they use atoms, Rydberg atoms, to control the internal states, or not internal states, to control the states of the cavities of the photons. So okay, so this has been done already, works well, but works for not so many qubits, let's say. For the cavities, typically on the order of 2, and for trapped ions, 20, or maybe a bit more, maybe 40 now, but still the current challenge is to scale this system more. Okay, and there are many candidates for scaling the system. We typically group them in two groups. So this one are the atomic, molecular, and optical systems, like ions, atoms in optical lattices, photons, okay, and solid-state systems, like superconducting circuits, quantum dots, which are very similar to standard classical computers made of semiconductors, or hybrid is like combining, let's say, quantum dots with photons, like in nanophotonics, and many, many, many more that I cannot just say here. And this is a picture how this type of experiment look from outside, so that you can see how complicated this can be. For instance, optical experiments can have many beam splitter mirrors, phase shifted lasers, and so on. All of them need to be aligned. It's very hard to do. And solid-state systems, you typically need like a fridge, like a cryogenics to cool these samples and avoid thermal fluctuation or thermal excitations and so on, and microwave controls. Well, and already there has been a lot of progress, and there is a lot of companies and public investment on this, like from Europe, US, China, a lot, and companies like Google, IBM, Intel, and also startups working on this now. And to date, the quantum devices that are largest so far are Rydberg atoms in twistor arrays. You can see there, where I say 2D, this is like a 2D array of atoms trapped in optical potentials, and they can even control this in 3D. For instance, the group there in Paris make a Eiffel Tower out of atoms there. This is just to show that they can control, but of course the Eiffel Tower will not be used for quantum computing, but the 2D setup, yes. And superconducting circuits, the biggest so far, there is 400 qubits. It has been reported by IBM, but it's still noisy and it's hard to do like clean computation with this, so it's still work in progress. And the ultimate goal in this field is to do quantum error correction. This means that you can use 100, let's say a group of qubits, let's say 1,000 physical qubits, to implement one effective qubit, like it's called a logical qubit, which is well, sorry. So use many qubits to implement one logical qubit, and with that you can correct the errors. If there are errors and decoherence, you can correct that and have a very good qubit made of many, let's say 1,000, but you need on the order of 1,000 of these to do an actual computation. So at the end, you need to scale the system on the order to 1,000,000 of qubits. This is like the long-term goal in the field. And later, to maybe we can imagine to have a quantum internet which is connecting these quantum computers in many parts of the world by optical fibers or satellites, I don't know, and do quantum communication between the computers. And there is still a lot of physics to discover in this field. It's not just technical details and add more funding and more money only, so it's really, we need to find new ways to do the quantum hardware to scale to these sizes. And this is where we work, and also many people in the group. And now related to my research, in specific, what I do in particular is quantum optics theory applied to quantum hardware. Okay, and my general objectives is to build theories or techniques to characterize and model this quantum hardware under realistic experimental conditions like noise, decoherence, and so on, taking into account that, and try to see how they work in reality. Design and propose new quantum devices that have new capabilities or are improved compared to the one that were already proposed before, and try to look for groundbreaking application in quantum information processing if we realize one of that. So this is what I try to always to do, and I work with a strong connection to experiments, especially with quantum nanophotonics and superconducting circuits. I try to apply my knowledge in these systems. Okay, and okay, I divide my research in 3 lines. This I want to sketch here. So one is what I call quantum nonlinear optics, and here the idea is to encode quantum information in photons and build these photonic quantum circuits which I have in the left. Here you have photon sources where you input photons, and you have beam splitters to prepare superpositions and measure that. And the challenge here is to make two photon gates, so to engineer interaction between photons. And for that we need quantum light matter interfaces like what I show here, like coupling these nonlinearities to photons and try to make interaction between them. This is the challenge that we try to face here. And the second line is what I call characterization and design of QND measurements. Here we can consider a superconducting quantum computer, and they have different steps to do a computation, like initialization, gates, and measurement at the end. And at the moment, the error in the measurement, you can see, is on the order of 1%, which is the largest in the whole device. And that's not a problem if you do just one measurement at the end. But if you need to do many measurements in between the calculation, which is for the quantum error correction codes that we need to do at the very end for quantum computation, then you really need to improve this error and reduce it a lot. And this is what I work in this line, to developing methods to characterize and reduce measurement errors in real superconducting devices. And the third line is about quantum topological photonics and directional devices. And here what we do is, the thing is, topological physics is not only restricted to electrons and condensed matter systems, but also to photonic systems. And for instance, here there is an array of optical cavities that are coupled together, and the light is sent in one port and is retrieved in another port, and you can see there is a photonic edge state that circulates in this device and doesn't go to the bulk. And this is because of the topology of the device. And this can be explored with photons at the quantum level, with not so many photons. And the challenge here is to, well, one of the challenges, there are many challenges, but is to discover new topological quantum phases of photons and to build directional devices. So you could use the topology to build a directional device. A directional device is some quantum device that works in a preferred direction and is very useful to protect the system in the opposite direction. For instance, if there is noise coming from the opposite direction, this will be suppressed. And in the right direction, this will be only act in the way you want, the direction you want, let's say. Okay, I don't know what we are with time. So I would just, at the end, just sketch some results I have found in this. Fine? Huh? Oh, okay. Yeah, I was talking too fast. Okay, so in the 10 minutes at least. 10 minutes. Okay, so in the line of quantum nonlinear optics, one of my first important results was together with Juanjo, which was the first project we worked together when I came to Madrid, and we developed something that we call multi-photon scattering tomography, which is basically a method to reconstruct the scattering matrix of an arbitrary quantum emitter, for instance, a two-level system, coupled to a waveguide, but can be any other system that scatters light. And we found a way that that you measure certain correlations that are easy to measure at the output, and from that, you can obtain the multiphoton scattering matrix of the device. And this is important because it's valid also when there is noise and decoherence in the environment, and therefore you can use this to try to understand nonlinear photonic devices in photonic circuits and see where the error comes and so on. That result was kind of motivated me to apply to a Marie Curie fellowship, and this was the work that part of the work I did during this fellowship, which was to try to realize this protocol in an experiment. And this we did in collaboration with Hanna Lejanik and in the group of Peter Lodal in Copenhagen. They on the left have the work that we really tested this protocol in experiment with a quantum dot coupled to a photonic crystal waveguide. We had to adapt this protocol to do this with photodetectors, because at the first we were thinking on superconducting circuits, but at the end it was possible. We could, for the first time, this is the small. I don't know. The small plot below on the left is like with the signature, the experimental signature that we could extract a genuine two-photon correlations from the quantum dot coupled to the one or two photons. And on the right is it's like a follow-up work that we did, which basically we have in the input a wave packet instead of a continuous monochromatic field, and this wave packet interacts with the quantum dot and changes it, and we create correlations on the photons at the output. We could characterize these correlations at the output, varying the width of the pulse, and this was very important experimentally because it's kind of very hard to do, and they show it for the first time also in these setups. They have this level of control. And in the second research line about characterization of QND measurements, here I collaborate with Luciano Pereira, who is doing his PhD thesis on this, and also with Juanjo. And basically our main result here is that we develop a method to reconstruct the measurement processes, or the process operator of a measurement, basically. Okay, of a QND measurement, which means that the measurement does not destroy the quantum state. You can measure again the state after the measurement. And for instance, here is a plot of the matrix representing this measurement process. And on the right, we also apply this method to a real IBM quantum device. This was mainly done by okay, the application of this was done by Luciano, who's very expert on IBM Q. And here, for instance, we applied this to a device of 7 qubits. You can see there in the figure. And we could really see which qubit is the measurement of which qubit is better than the others, and try to find the sources of errors in that device. Okay, and also in this line, I have collaborated with a group in Institut Nellinger Noble, and there with them we have proposed a way to do a QND measurement of a qubit using a cross-kerr coupling, which is different than the standard way that this is done. And with that, we could show that there is a 99% fidelity of QNDness in this, which was very important for the community because the highest value so far obtained, and also with a fast measurement of 50 nanoseconds. And in the last research line, I want to comment here. This is first we did in collaboration with Diego and Juanjo. We developed like a theory, a quantum theory, to characterize topological amplifiers. Okay, and we show that it is possible to get exponential gain in the amplification, and at the same time to have quantum limited noise. And very recently, collaborating also with Alvaro and with Alejandro, We have put 2 new works in the archive. They are currently under revision, where we propose a very practical way to build a near-ideal superconducting amplifier based on these ideas of the topology. And if realized, this is still a proposal, will be the first amplifier that, well, if it is realized now, will be the first amplifier that can be broadband, directional, can have gain, low noise, and everything to be on chip. And there are already companies that are interested and contact us to really to see if this is possible. We are working with them. Well, this is one to mention you about my research. So in summary, I work on theoretical quantum optics applied to quantum technology, especially in nanophotonics and superconducting circuits. And I developed these 3 research lines of quantum nonlinear optics, quantum 2D measurements, and non-reciprocal devices. And I want to knowledge of my collaborators of this work. Thank you very much.